So, inequalities on graphs. Just a quick summary of what we did in the last session. Hello. Yes, early. We talked about, what did we talk about? We talked about quadratic inequalities. And we looked at examples like a quadratic and a linear inequality, and finding the set of values that satisfied both of those inequalities. So now we're going to be graphing these things. So inequalities on graphs. And just a quick note, these live streams, I've been posting them as videos, but now I'm going to post them as unlisted videos. They'll still be in the playlist, so you need to go to the playlist to view them. That's just so that it doesn't get too spammy, so I'm not publishing all of these live streams on your YouTube feed. I'll just publish them as unlisted, so if you want to watch the videos, go to the playlist. So this book again is the Edexcel and AS, Edexcel, AS and A-level mathematics, pure mathematics, year 1, published by Pearson. Looks like this for the new specification. Hello. Okay. So inequalities on graphs. You may be asked to interpret graphically the solutions to inequalities by considering the graphs of the functions that are related to them. The values of x for which the curve y equals f of x is below the curve y equals g of x satisfy the inequality f of x less than g of x. Year 1, it's referring to the first year of the A-level course. Technically year 12. But that's what they mean when they say year 1. They probably should have written year 12. It's a little bit confusing. The value of x for which the curve y equals f of x is above the curve y equals g of x satisfied the inequality f of x greater than g of x. So they're introducing this function notation again, which we've already encountered, and hopefully you're already comfortable with that. Okay. F of x is above g of x where x is less than 2 and x is greater than 5. These values of x satisfy f of x greater than g of x. So here we have a graph, the quadratic and a straight line. You can see where f of x is greater than the straight line. In other words, where the quadratic is greater than the straight line is above in these dark blue regions. So when we're saying greater than, we're talking about the y values, right? So wherever the y values are greater, and f of x is below g of x when x is between 2 and 5, these values of x satisfy f of x less than g of x in this light blue region. The solutions to f of x equals g of x are x equals 2 and x equals 5. That's where the graphs intersect. We've talked about that in previous sessions. I am using Notability. It's an app for Mac computers, I think. I'm not sure if it's on Windows computers as well. There's nothing particularly special about it. I just found that it does everything that I need, but there's plenty of apps that do the same thing, I think. Okie doke. So here's an example. We have L1 has equation y equals 12 plus 4x, and L2 has equation y equals x squared. So there's the quadratic, there's the straight line. It asks find the coordinates where the graphs intersect. We've done that, we know how to do that already. And write down the solutions to the inequality 12 plus 4x greater than x squared. So that's where that straight line is greater than the quadratic. So here, the way they find the points of intersection is to let the two equations equal to each other. So 12 plus 4x is equal to x squared. – that's going to give you the x values of where they intersect. right? Because where the graphs intersect, they will have the same y coordinates. So these two y's will be the same. So we get values of x equals 6 and x equals -2. Substitute that in to get the y values. So then we get the coordinates of where they intersect. And then the inequality of the straight line greater than the quadratic, that is between those 2 points. So let's have a look carefully at this graph. Whoops. You can see the red line is the quadratic, the straight line is, the black line is the straight line. Where the straight line is above the quadratic, it's in here, in this section, between these 2 points. So to satisfy this inequality, we would say x is between -2 and 6. Okay. Hello, hello. The next, actually, so then it gets straight into the exercise. So let's get straight into some questions now. So we're doing exercise 3F. We have L1, which is 2y plus 3x equal to 6, and L2, which is x take y equal to 5. And it says the diagram shows a sketch of L1 and L2. So red is L1, black is L2. And it says find the coordinates of P, the point of intersection. This is like solving linear simultaneous equations, and we did a whole section on that already, so I won't spend too much time talking about this. I won't need that graph, by the way. So how do we solve this? We could use elimination, or we could use substitution. Which way is going to be best here? So I might rearrange L2 so that it is x equal to 5 plus y, and then substitute that in to L1. So then if I use substitution, use this value of x, substitute it into this equation, we get 2y plus 3 times 5 plus y equal to 6. And then 2y plus 15 plus 3y equal to 6. And then 5y equal to, I feel like I made a mistake already. Although, maybe not. 6 subtract 15. That is -11, so y is equal to -11 on 5. And if x is equal to 5 plus y, x is equal to 5 subtract 11 on 5, which is like 25 take 11. 14 on 5. Okay, that's a weird solution. That's the reason why I think I've done something wrong, but I don't know what I could have possibly done wrong. Okay. Let me get rid of this. No. Okay, so that is my solution to these simultaneous equations. In other words, where they intersect. So we can say the point of intersection is 14 on 5, negative 11 on 5. And then part B asks, write down the solutions of the inequality negative 3 on 2x plus 3 is greater than x take 5. This is another way of writing L1. So they've rearranged L1 in the form negative 3 on 2x plus 3. And they've rearranged L2 so that it's y equal to x take 5. So where is the red line greater than the black line? That is less than the point of intersection. So everything over here to the left of where they intersect. So this was the point of intersection. The x coordinate is what we care about, the 14 on 5. So the solution to the inequality will be x less than 14 on 5. And that's it. So we're done for question 1. I'm going to go ahead and check that because I just want to make sure I didn't make some silly mistake with that solution there. Okay, so they've written it as decimals. 11 on 5 is the same. No, it's sorry. Yeah, it's the same as. No, it's not. I have made some error. What have I done wrong here? Have I written the equations wrong? So let's just write down the answer while we're here. We had 3.2 and negative 1.8. This is a great start. Oh, 6 take 15. Thank you very much for picking that up. 6 take 15 is negative 9. There we go. So as usual, I've made a silly numerical error there. So y is negative 9 on 5, which is negative 1.8. And then x is 5 take 9 on 5, which is 25 take 9 is 16 on 5, which is 3.2. Okay then. So then this should be negative, 16 on 5 and negative 9 on 5. Awesome. And this should be x less than 16 on 5, which is the same as less than 3.2. Must be a Friday. Okay. So that was question 1. This is a short exercise here, just a couple of questions. So let's go into question 2, and I've got all these graphs in the way because I thought I'd need a lot of them. Okay, on to question 2. Question 2 says, for each pair of functions, sketch the graphs of y equals f of x and y equals g of x on the same axes. Find the coordinates for any points of intersection and write down the solutions to the inequality f of x less than or equal to g of x. Okay, so we have a bunch of functions here. Let's just do a and b. So a, we have f of x equal to 3x take 7. Oh, this is a linear one. Let's do some quadratic ones. So let's start with c actually. So f of x is equal to x squared plus 5, and g of x is equal to 5 take 2x. We need to sketch these. Okay, so let's bring this up again. Let's see. So that'll be my y-axis. This can be my x-axis. F of x is x squared plus 5. So actually, let's shift this x-axis down a little bit. Can I even do that? No. Because I can see the y-intercept will be at 5. So shifting that down so I have a bit more room. 1, 2, 3, 4, 5. And then this is going to be a normal quadratic. So the next one will be at 6. And then 5 plus 4, 9. So 6, 7, 8, 9. And so on. So it's going to look like that. So it's basically x squared translated up 5 units, right? So this is x squared plus 5. And then the straight line is also has a y-intercept at 5 and a gradient of -2. So let's do that in a different color. This will be like this. So it looks like we'll have 2 points of intersection just from this rough sketch. And we need to go ahead and find what they are. This is like solving quadratic inequalities, and we've done this already. So the first thing we do is we can let them equal to each other, let the two functions equal to each other. That is when they're going to intersect, when f of x equals g of x. So I might just make a note of that. So they intersect. Let me just neaten that up a little bit. Intersect when g of x equals f of x. So this is when x squared plus 5 equals 5 take 2x. And then we will have x squared plus 2x equal to 0. And then x multiplied by x plus 2 equal to 0. Hello, hello. And then x equals 0 or x equals -2. And then we need to find the y-intercepts, the y coordinates. So if x equals 0, y will equal 5. And when x equals -2, y will equal 9. So the points of intersection are 0, 5 and -2, 9. And then we need to write down the solutions of the inequality f of x less than or equal to g of x. Based on the graph, remember this was f of x. Should have written that in. This was f of x. It's less than g of x when it's below the straight line in terms of the y-axis. So it's below the red line, so it's in between those points of intersection. So we would say then the solutions are And we don't need to use set notation, so we would say this is for part 3, when x is between -2 and 0. And I'm using equal inequalities because that's what they used in the question, f of x less than or equal to g of x. Okay. Alright, they all look fairly similar, so I think that's a good enough example for question 2. Okay, let's go into question 3 then. Question 3 says, find the set of values of x for which the curve with equation y equals f of x is below the line with equation y equals g of x. Okay, so these are, I guess, just getting slightly more complicated. Which one could we do? Maybe E. E looks sort of interesting. So E, we have f of x equal to 3 on x squared, take 4 on x, where x is not equal to 0. And g of x is equal to 7x plus 13. So firstly, let's try to sketch these. This one's going to be kind of hard to sketch. Oh, we don't have to sketch these, sorry. We just have to solve them. Okay. Okay, again, let me get this out of the way. All right. Well, the first thing we can say is we need to find the points of intersection. This is when f of x is equal to g of x. So I'll just make a note of that again. Intersect when f of x equals g of x. That's when the graphs cut each other. So we'll have 3 on x squared, take 4 on x, equal to 7x plus 13. Okay, this is going to be okay. So what we should do here is multiply through by x squared to get rid of these denominators. So if we multiply everything by x squared, we're left with 3 take 4x equal to 7x cubed plus 13x squared. So we're actually going to get a cubic. Oh, I've written the wrong function. I've written this one. Whoops. Apologies. This should be -1. Okay. All right. This is not a disaster. So I just have to replace that with a -1. And this is going to be -x squared. Okay. That makes things easier. Then we have x squared plus 3 take 4. Oops. Let me write that around the other way. X squared take 4x plus 3 equal to 0. And then we could factorize this into x take 3, x take 1. So then our points of intersection are at x equals 3 or x equals 1. And then let's find the y. Well, the y coordinates must be -1 because that will be a horizontal line. So wherever that intersects the quadratic or whatever this is must be at -1. So the points of intersection are 1, -1 and 3, -1. Hello, Hitesh. And then we want the set of values of x for which the curve f of x is below the line. For that, I kind of want to know what this would look like. I think it's like, we looked at one of these the other day, and I think it's like this. So we would have a line at -1, -1, and the graphs would be below those. But then, no, this is not a function. I'm wondering what this 3 on x squared take 4 on x would look like. Well, what we could do is to determine where it's below the line, we could plug some values into f of x. So we could put, say, 0 into, sorry, it's not 0. We could put -1 into this. So f of -1 and see what we get. So this would be 3 plus 4, which is 7. This is greater than -1, so that's greater than g of x. And then let's put something greater than 3, so f of 4. This would be 3 on 16 take 1. Which is a -13 on 16. Okay. Just to be clear what I'm sort of wondering here. So I have a line at -1 on the y-axis. This is g of x. And I have some function, I'm not sure what it looks like, but at x equals 3, it's negative. Oh, that's still greater than -1 though. Oh, okay, yeah, that's fine. That's still greater than -1. Okay. Everything's fine. So then, then I have determined that the function f of x will be greater than g of x when x is less than 1. So x is less than 1 and x is greater than 3. So that would be my solution there. All right. This is when f of x is less than g of x. When x is less than 1 and x is greater than 3. Okay, that was kind of interesting. So let's just go ahead and check those two to make sure we did those correctly. Then I'll move on to the challenge. this was 3f. Hopefully I didn't make any mistakes this time. F, and I did 2c, this was the graph. That looks good. Then my points of intersection are 0, 5 and negative 2, 9, and my inequality is x between negative 2 and 0. Great. And then 3e was x between 1 and 3. Right. Okay. Oh, it's I just got the inequalities around the wrong way. So, yeah. So it's pretty clear what I've done wrong here. It was when f of x is less than g of x. This, what I've written is when f of x is greater than g of x. So I just mixed those two things up. Okay. So all of the working out was fine there. It's just at the end I made another mistake. This is not a good day. All right. Okay, well, at least I'm you know, they're small mistakes. They're just like not major things. So I'm happy with that. Hello, hello. Okay, we're on to the challenge. And this graph paper again is getting in the way. So let's have a go at the challenge then. This one here, it says the sketch shows the graph of f of x equal to x squared take 4x take 12. That's the black quadratic. G of x is equal to 6 plus 5x take x squared. That's the red one. And it says find the coordinates of the points of intersection. Okay, we know how to do that. And then it says find the set of values for x which f of x is less than g of x. Okay. So let's write down these functions. And if you want to have a go at this, then I would think that would be a good idea to challenge yourself. So points of intersection. Can somebody tell me, if you are there and listening, what is my next step here to find the points of intersection of these two quadratics? If anyone wants to chime in. What should I do to find where these two functions intersect? I've already said it a couple of times in this stream. Okay, possibly everyone's fallen asleep. So the functions intersect. Functions intersect when what? The functions intersect when, I'm hoping somebody says something. Okay, I got tired of waiting. Functions. The functions intersect when f of x equals g of x. So remember, these are, you can think of these as like two graphs. When they cut, or they've already done a picture for us, when they cut each other, you can think about that as where the functions are equal. So at the points where they meet, they you know, they're the same, right? It's like if you're walking to meet your friend. You know, they walk from their house, you walk from your house. The point where you both meet up, that's the same place. Yeah. You know, you're not going to say, oh, let's meet up at the McDonald's down the road, and then your friend goes to KFC and you go to Burger King. You both go to where you want to meet. So it's the same with functions. When they intersect, it's where they're both equal. So the functions intersect when f of x equals g of x. So then we can say x squared take 4x take 12 is equal to 6 plus 5x take x squared. Hello, hello. Hello, Abdallah. And then we solve this equation for x. So bring that x squared over to the left-hand side, 2x squared. Take 9x, 12 take 6 is negative 18. This equals 0. And then we have a quadratic, hello right tree, that hopefully we can factorize. So are there factors of 18 and 2 that make 9? So factors of 18 could be 6 and 3. And if I multiply the 6 by 2, that would give me 12. Oh, you could, except 9 does not divide by 2 evenly. So, and then we get 3. So 12 and 3 make 9. If it's a negative 12 and a positive 3, then I'll be able to factorize. So I believe I can factorize this to 2 multiplied by 6, that's a negative, plus, whoops. Whoa. Plus 2x. Plus 3x, sorry. Will expand out to 2x squared, take 9x, take 18. So then my x coordinates of where they intersect are negative 3 on 2, or x equals 6. Oh, my writing's so messy, yeah. That's meant to be a 9. And I am again going to move these down. Okay, so they're the x coordinates of where they intercept. Then we can go ahead and find the y coordinates by substituting them into either one of these. We could say we could find f of x, f of negative 3 on 2, which is kind of annoying because we have to plug a fraction into all of this, but let's go ahead and do that. So 3 on 2 squared is 9 on 4. Take 4 times negative 3 on 2, take 12. This is 9 on 4, take plus 3, plus 6, take 12. And then it's 9 on 4, take 6, which is what? That's 2. 2 and a quarter, take 6. Negative 3 3/4, which is negative 15 on 4. This is this book here, Pure Mathematics Year 1 AS. Should say Year 12, but Year 1 of the A level specification. It's one of the only textbooks really made for the new linear specification, so that's why I'm using this. And I just bought it, so I'm working through it to get to know, like, you know, to do it, I guess. Okay, so I have one point of intersection. The other one is when x equals 6. So f of 6 will be 36. I'm plugging it in here. Take 24, take 12. And that's going to be 0. So it looks like that looks accurate according to the graph. So this point here that looks like it's on the x-axis, that will be at 6, 0. So then I can say points of intersection. I'm on part A still, finding the points of intersection. So this is negative 3 on 2. Oops. Negative 3 on 2, negative 15 on 4. Okay, according to the graph, that looks like it could be right. And the other one was 6, 0. Okay, then part B says find the set of values of x for which f of x is less than g of x. The black quadratic was f of x, and the red quadratic was g of x. Let's see if I can get this right this time. So where f of x is less than g of x will be between those points of intersection, where it's below the red line. Okay, so in set notation, we would write it like this. You have those squiggly brackets, and then x colon between negative 3 on 2 and 6, and squiggly brackets. All right, so another challenge done. Gotta say, I'm a little bit disappointed in these challenges. Personally, I mean, I think they could be a little bit more challenging. But I guess they're okay. All right, let's just see. So we've got negative 1.5, negative 3.75. That's the same thing as those fractions, and 6, 0. And then x between negative 1.5 and 6. Okay. Good, good, good. Okay, we're on to regions now. We are on to regions, so we'll be shading some graphs, I believe. Oops. So let's see. We're on to 3.7 regions. Thank you all for all of you joining in, by the way. Okay, so regions. You can use shading on graphs to identify regions that satisfy linear and quadratic inequalities. Y less than f of x represents the points on the coordinate grid below the curve y equals f of x. y greater than f of x represents the point on the coordinate grid above the curve y equals f of x. So if we have some quadratic f of x, the yellow part would be y greater than f of x, and the clear part here would be y less than f of x. If y greater than f of x or y less than f of x, then the curve y equals f of x is not included in the region and is represented by a dotted line. If y is greater than or equals to f of x, or y is less than or equal to f of x, then the curve y equals f of x is included in the region and is represented by a solid line. Okay, so when drawing the graph, either draw a dotted line or a solid line, depending on what sort of inequality you have. So here's an example. On graph paper, shade the region that satisfies the inequalities y greater than or equals to -2, x less than 5, y less than or equal to 3x plus 2, and x greater than 0. This has all been included in the GCSE specification now, so if you've done GCSEs, you would have or should have done this already, but it's always good, of course, to get the revision. So give some explanations here. Draw the dotted lines, shade the required region, draw the solid lines. Then another example with a quadratic. On graph paper, shade the region that satisfies the inequalities 2y plus x less than 14 and y greater than or equal to x squared, take 3x, take 4. So there's the quadratic. Here's the straight line. It's a dotted line because this is less than, not less than or equals to. Wow, that's really annoying. Hang on a sec. I guess someone's decided to do some drilling today. Hopefully it doesn't go on too long. Okay, let's do some questions then. The Taylor series? No, that's further maths. Apologies about the noises in the background. Hope they're not too loud. Okay, so we're going to be doing a lot of sketching. That's why I have all of these grids. Okay. Let's see. Question 1. We have y greater than x take 2, y less than 4x, and y less than or equal to 5 take x. Let's draw our axes. This line will have a y-intercept of -2 and a gradient of 1. Hopefully you're comfortable with drawing straight lines, and this is just greater than, so it needs to be a dotted line. Okay, so that is the line y equals x take 2. Y less than 4x, that will be lines going through the origin at 0, 0 and have a gradient of 4. And have a gradient of 4. So up 4 across 1, up 4 across 1. Again, this is a dotted line. So I'll just draw it in like this and then rub some bits out. Okay, that's meant to be a dotted line. You get the idea. And then we have a solid line, 5 take x. So this is a y-intercept of 5 and a gradient of -1. So that will be like this. And we need the region. Greater than x take 2, so above this line, less than 4x, and I should label the line so I remember which is which. This was y equal to 4x, and this was y equal to 5 take x. So I need the region below y equals 4x and the region less than 5 take x. So it's going to be in this little triangle here. Okay, that is my shaded region. Not too bad. The next question looks fairly similar. I'll leave that for you to do either now or at a later point. 3 looks like we'll have a quadratic, so let's have a go at question 3 as well. So we might need to simplify them a little bit first. Okay, so we have the inequality y less than 3 take x and 2 plus x, and y plus x greater than or equal to 3. Greater than or equal to 3. We could write this as y greater than or equal to 3 take x. So then I can see that that's a straight line with a y-intercept of 3 and a gradient of -1. And this quadratic, before I expand it out, I can see that the x-intercepts will be at 3 and -2. And it will be a negative quadratic. And if I expand it out, so I could write this inequality also as y less than 6 plus 3x take 2x take x squared, which is, actually I could have written this as x in the middle. So 3x take 2x is just x. And then the maximum, the vertex, is negative, sorry, that's not right. Negative, oh yeah, it's a half. And I'm just wondering, okay, so yeah. So we need to remember back to sketching quadratics and how we did that. So there was a couple ways we did it. We kind of wrote it in a different way, and then we found the maximum or minimum, and then we were able to sketch it. So that's what I'm doing here. The vertex is equal to negative b on 2a. They are the coefficients in this quadratic. This the b is 1, a is negative 1, so this would be 1 on 2. And then we can find the y value of the vertex. If we substitute that half into this equation, we would get 6 plus a half, take a quarter, that's like 6 1/4. So that would be up here. Oops, yeah. Up here somewhere. Okay, so this is what my quadratic would look like. Something like this. And then my straight line is, the y-intercept is 3 and the gradient is negative 1. So that would look like this. Okay. And then we need to shade the region where it is less than the quadratic and greater than the straight line. So above the straight line is here, below the quadratic is in here. So we need to shade that region there. All right. Okay, so that's a quadratic and a straight line. Here's an example with 2 quadratics. So that's going to be fairly similar. You just sketch the 2 quadratics and then shade the required regions. Let's have a go at 5 because it has 3 inequalities. So question 5. Let's move this down a little bit. We have y greater than x take 3 all squared. Y plus x greater than or equal to 5 and y less than x take 1. We could write this as y greater than or equal to 5 take x, just to make it easier to graph. And this one will have if we expanded that out. Oh, sorry, this means that we have the 1 repeated root. So this means it just touches the x-axis at -3. So let's draw our axes. Again, whenever you see a quadratic written like this, it means that it has just the 1 point of intersection with the x-axis. And what else? And I guess, well, if we, yeah, and then otherwise it's a normal quadratic. So you go down 1 and then 3 and then 5, just as you would, like if it was just x squared, you should know what that graph kind of looks like that. Okay, so that would be the graph of y equal to x take 3 all squared. Then the straight line 5 take x, y-intercept of 5, a negative gradient, be over here somewhere. Okay. I just realized that this should be at +3, not -3. Damn. So it's x take 3 all squared. That means the solutions are at x equals +3. Okay. So I just need to do all of that again, except over here. Okay. Done. And then y equals x take 1. This is a y-intercept of -1 and a gradient of +1. And so they're my three graphs. This one's y equals x take 1. This one is y equals x take 5 take x. And then let's think about the regions. Oh my gosh, I've realized I messed this quadratic up. It should be a positive quadratic, not a negative quadratic. I'm not sure why I was drawing it that way. Dear, oh dear. It should be up this way. Okay, finally, I think I've got all of those graphs correct. And now let's think about the regions. So we have y greater than the quadratic, so above the curve, y greater than or equal to the straight line 5 take x. Greater than, okay, so it has to be above both of those, so up here. So that's above both the quadratic and that straight line, and it's also less than x take 1. Ah, so putting all those things together, then that must be that little region in there. So that's above the quadratic, above that straight line, and less than that straight line, x take 1, sorry. Cool. Okay, so that was a quadratic and 2 straight lines. Question 6 has 3 straight lines. Oh, it says the sketch shows the graphs of the straight lines y equals x plus 1, y equals 7 take x, and x equals 1. Work out the coordinates of the points of intersection. Okay, we could read them straight off the graph. That would be 1, 2, 1, 6, and 3, 4. And write down the set of inequalities that represent the shaded region. So that would be y greater than x plus 1. What about when it's a vertical line? What do we do when it's a vertical line? Well, it's going to be y greater than x plus 1, y less than 7 take x, and something x greater than 1, possibly. We couldn't have a y value, so maybe you have an x greater than 1. Okay, so for question 6a, points of intersection are 1, 2, 1, 6, and 3, 4. And the inequalities are y greater than or equal to x plus 1, y less than or equal to 7 take x, because these are solid lines, and then I'm going to say x greater than 1, but I could be wrong. So I want to check that. Question 6. I'm not sure what you do with a vertical line, to be honest. And I'm going to have to go because that noise is way too annoying for me to deal with. Question 6. Yes, it was x greater than or equal to 1. So if it's a vertical line, you have to consider the inequality in terms of x, not y. And then it's y less than or equal to 7, take x, and y greater than or equal to x plus 1. Okay. Oh my god, I cannot believe. I don't know what this guy is drilling. He's been drilling for about, I don't know, a good 3-4 months doing the same thing. And the times change during the day. Sometimes it's at like 8 p.m. at night. Sometimes it's now. I have no idea what he's drilling in his apartment and hammering. Anyway, that's a fair bit on regions. There's a couple more questions. We can finish those off next time. And then we'll be on to chapter 4. Okay. As always, thank you for your company today. Appreciate it. If there are any questions just before I go, feel free to post them. I'll hang out for another 5 minutes and then I'll head off. Alrighty, thanks for tuning in, guys. I'll see you next week. Bye for now.